Live. And we're live. Welcome everyone to the 33rd Data Science Leuven meetup already. It's the first meetup of 2021 and it's still on YouTube. As you can see, we're not that stuck in Leuven. We think that depending on the vaccination strategy of Flanders and Belgium will probably be remote until end of June. So our first real physical meetup will be in September again. But let's see how that goes. So we're kind of getting used to the remote meetups by now. We have with us three very exciting speakers, Jannes, Stijn, and Geert. Hello. I have prepared one slide to introduce them, so I'll quickly do that. Share my screen. Here we go. Yep. Now you see an inception thing. Like it's All right, so who do we have with us tonight? I hope I copy pasted all of this correctly. Yeah. So first off is Jannes from the University of Antwerp. He's going to talk about causal machine learning. Next is Geert Baker from Kronos, and he will show us how he uses Kubernetes to deploy ML models and API using GitOps principles. And then finally, last but not least, we have Stijn with us, Stijn from Accenture, and he is going to talk about honeybees and IoT sensors to help solving biodiversity. So it's a very let's say mixed audience tonight, or mixed talks. As usual, if you have questions, post them in the YouTube chat. There is some delay between the YouTube chat and us, so it might take a minute before we see your question. But so if the presentations are ongoing, just drop a question in the chat, and then we can see if we can answer them. I'll be the moderator. We also have Istvan with us to help moderate if needed. And besides that, I think we're ready to go. Jannes, you're first up, so it's up to you. Feel free to get started.
Can you see my screen in the meantime?
Yeah, there is your screen.
Okay, so hi everybody. My name is Jannes Nees and I want to talk about, I just noticed causal machine learning. And so, okay, this work is not just done by me, it's done by a group. So I work at ID Lab Antwerp. And so we have a group working on causality. We call it the scientific machine learning group, or the S2ML group. The big boss at ID Lab is Steven Lautry. He's my direct boss, but I'm leading the sub-team of scientific machine learning. The work that I'll be talking about today is mainly done by this very good student, Bart Busman, who's done a lot of good work in the last year. So, okay, these are the topics that I want to tackle today. First, I'll give an introduction about correlation versus causation and why you might want to care. Then I'll talk about the reason why traditional machine learning can't really capture causation that well. And I'll talk about causal models, and finally I'll end with some of our very recent work. So, okay, let's start with a very simple example. So here we have on the y-axis the number of Nobel laureates as a function of the coffee consumption per capita in certain countries. So based on that, you see a certain correlation. So you might, if you don't know what the difference is between correlation and causation, you might, and people have done that because this is a figure from a paper, people have concluded that the number of laureates depends on the coffee consumption. Of course, if we think about this a bit further, we know that there is no direct well, we assume that there is no direct causal link between each other, but both are rather influenced by maybe a third variable. So, for example, the number of research institutions within a country. So let's take this very explicitly and let's look at an example. So we want to generate a figure like the one on the previous slide. So let's assume that we want to generate a two-dimensional Gaussian model with some correlation. So the variables are x and y. And I asked this to a bunch of students or a bunch of people who can code, and I asked them, okay, generate a figure like this. If I give this to a lot of different people, they might come up with different answers. So there are particular particularly three answers that I want to talk about. So a first group of people could generate variable x first from a random distribution, so just a normal distribution, and then based on that use it as an input to generate y to generate the correlation. You can also do the opposite and start from y first and then generate x. Or maybe a third group of clever people could say like, okay, there's not really a reason to first do x and then y. I could rather start with a third variable, a confounder z, which has a normal distribution, and then use that one as an input to generate y and x. Both of these are a good option because they all generate the same distribution. They all generate the distribution that I want, being the two-dimensional Gaussian with some correlation. But if I represent them in a graphical way, they definitely don't look the same, right? So this is just a schematical way of showing that in this case, I generate x first, and then based on that, I causally generate y. So there's a causal relation, and y is the effect, and x is the cause. And here it's just the opposite direction, and in this case I have a third variable that influences both of them. So from the observational point of view, there's no reason to choose any of these over another one. So okay, I introduced this language of these graphs because they essentially tell us which variables are causally determined by which other graphs. And in general, these graphs are, well, they are directed because causality has a certain direction. They are acyclic because, of course, if they causally influence each other, there cannot be a cycle in this network because otherwise we would have this sort of paradox where things keep influencing each other. And we in general refer to them as DAGs. Now, probably most of you already think about Bayesian networks because most of us learned this in university. But Bayesian networks, what they describe is they mainly describe observational distributions. So they basically say how all the three variables in this case are connected to each other, and they describe the independencies between them. So, for example, if I measure a variable z, what is the observational distribution of these two other variables? Are they still independent? Are they connected to each other or not? Causal networks are the same with a few additions, in the sense that they capture what a Bayesian network captures, being the observational distribution, but it also does something more. It also allows you to capture interventional or experimental distributions. And interventional distributions are essentially those where you really start intervening on the system and where you take one of the variables, for example, and you put them to a fixed value. I won't discuss the last one, but let's go more into detail about what this interventional distribution is, because this really distinguishes observational Bayesian networks from causal networks. So let's go back to our example that we discussed previously, and let's take again these three scripts and that we use to generate correlated variables. And let's do the intervention x equal to 3. So to make it very concrete, let's assume, for example, that we have a data set where we measure plant height across the globe, and we want to look at the influence of the sun and humidity, let's say. Let's say that x in this case equals the humidity, making an intervention does not just mean that I'm going through this data set and only take those cases where the humidity has a certain value, because that's just computing essentially a marginal distribution. An intervention is really changing the mechanism. So it would, for example, come down to going somewhere on the globe and taking certain plants, putting it in the greenhouse, and manually changing the humidity levels. So, okay, what if I apply this to our three different distributions? Well, if I think about what this intervention really does, it changes, for example, the humidity, puts it on a certain value, which also means that in this case the humidity is no longer influenced by other factors in the network or in this experiment. So I can assume that in this network, all the incoming links into X, I can just remove them, because if I do this intervention, it's independent of it anyways, and then I can just propagate the information throughout the whole network to see what the final distribution is. So if I do this and I take these networks and I just remove the incoming links of X, what I notice is that these two types of networks, that they sort of factorize. So if I just look at the observational distribution of X and Y, here they are completely factorized, so they become rather straightforward and independent. While in this case, there is still a causal link between X and Y. And indeed, if I look at the mechanisms, those script that I saw before, and I just put that value X is equal to 3 to that fixed value, I indeed see that the interventional distribution, so this is what we call interventional distribution, that it's not the same for all these 3 scripts. And that's the main difference. That's the main thing that I want to take into account when I look at causal discovery. So, okay, but what's the advantage of looking at causality? Well, I think it's clear that it will result in better generalization. And this is all due to the invariance principle. It basically says that if I go and look in different environments, so that's usually, and in different environment is usually a different, doing a different intervention. So for example, a different environment could be if I take images from different smartphones, for example, a different environment could be the different smartphones. But this means that my distribution, my intensity, for example, it sometimes changes a bit. So I get slight changes in my distribution, but it doesn't necessarily change how all the items in my causal network are connected to each other. So to put it in a very specific example of, for example, trying to predict ice cream sales and the amount of ice cream sales, if I build a model that tries to predict the ice cream sales based on sunburn and the sale of sunburn, well, of course, I'm looking at a correlation. Well, it's definitely better to just look at how much sun we are predicting, because this is really a causal direction. And if we model, if we make a predictive model in the correct causal direction, then if I go to another environment, so one where, for example, a different country where sunburn isn't that much used, so it's not really a predictive variable anymore, then if I would just fit it at the amount of sun, then I would have been able to keep my model. While if I would have just captured the correlation, I could just throw away my model completely. There are some other advantages of using causal models, one being looking at simulations and performing interventions, really, and the other one being to extract expert knowledge from data. Most of the methods that try to do causal machine learning, they build on a couple of key principles, but the main one being this invariance or independence principle, which basically says that if I have a model, I build a model, and I go towards some other environment, then most of my functions, because all these links, they're not just an independence or a dependence on each other, but they also contain functions. Then I can keep most of the functions, but I only have to change a few of these links. And this is all based on the fact that independence, there is an independence between the cause and the cause-effect mechanism. So just to give you another example, why this is relevant, for example, say that I look at insurance, I build an insurance model, whatever you're trying to predict, and I build it in Belgium, and now I want to go to some other country, let's say Italy or so, then in that case, well, definitely the driving behavior is going to be different. If I make an insurance model for cars, driving behavior is going to be different. But for example, the effect of age, let's say, on driving behavior might still remain the same. So we definitely have some invariant properties. So some of the functional dependencies will remain the same, just that we have to fine tune it a bit to this different environment. And this is an essential link that was made rather recently, is that there is a connection between generalization of a model and causality. And the connection between them is invariance. So the thing that I was talking about is that if you go to a different environment, that there are definitely parts of your model should remain the same if you model it in the correct causal direction. For people who are interested, just Google invariant risk minimization, which was, I think, published 2 years ago or so, a new interesting topic that connects these two to each other. So let's go to traditional machine learning, because, well, when I was a data scientist working in industry, I was reading these tutorials all the time and blogs, and people were constantly talking about, correlation is not causation, and you should know the difference, and your model is probably using correlation. And I was always wondering, like, but I mean, first of all, okay, but why is it only using correlation? Should I just handle this as a data scientist, because that was always my idea, or are there methods against it? And also, how do I solve it, and how do I figure out when I'm using correlation and when I'm using causation? So let's take a very simple example. Say that I have a data set which has two input variables, x1 and x2, and then I'm trying to predict a variable y. I'm giving you the underlying causal DAG. So in principle, of course, normally you don't have this, but I'm giving you how they are causally related to each other. So it seems that if I want to model along the causal direction, I should regress y on x1. So then I know that I'm telling you already that my model will be much stabler in that case. So what I'm going to do is I'm going to build a linear model and that uses these two as an input and fit y. I'm just going to use the traditional empirical risk minimization. So for people who don't know this word, this is just optimizing a loss function for a training set. I'm also giving a very explicit formula for how I generate a data set. I'm generating x1 with some Gaussian with a given standard deviation sigma, which is then used as a linear input to y, and y then again generates x2. So I fit this model, and of course what I'm going to get is, well, in some cases, I mean, there's in principle no reason why I should take x1 as an input rather than x2. Because if you look at this, for example, x2 is a perfect predictor for y. So if I just use my traditional machine learning approaches, I'm going to just fit both of them, and I'm going to be dependent on both of these, on both x1 and x2. That's not a problem. The only problem happens when we, for example, go to a different environment. So we can simulate a different environment by, for example, changing sigma. Again, you could think of this example that I gave before of looking at different smartphones, for example, to take pictures. That's changing a certain distribution slightly. If I look at the model where I just fitted y and just took x1 as an input, then if I look at the optimal parameters, optimal coefficients, then I see that the coefficients alpha 1 and alpha 2 for my linear model, well, they don't seem to depend on sigma, so they don't depend on the environment that I look at. So if I would have fitted my model in one environment and I would just go to another environment, it would just completely work. I don't have to change anything. If I would have gone in the opposite direction from where causality is pointing, so if I would use x2 as an input, then there's a bit of a problem. So even though in one environment it looks perfectly okay, if I look at the optimal coefficients of my linear regression, then I see that my coefficient depends entirely on the environment. So of course, if I go to a different environment, I'm screwed. I have to throw away my model, and I basically have to start from scratch again and just refit it. So this model is not invariant. It's not robust to changes in my data set. So okay, can I obtain causality? So can I fit causal models from observational data? Well, in principle, no. In principle, causality, there's a statement that says there's no causality without interventions. So I have to do experiments, change certain variables manually, really do an intervention in order to be able to discriminate and extract causality, just as in this example that I gave earlier with the correlations and these three different scripts. In many cases, of course, it's not possible to perform an intervention. So think about, for example, earth sciences, where I want to study the effect of CO2 on the temperature. Of course, I cannot just, even though we're doing this, but we cannot just pump a lot of CO2 in the air and see what the effect is on the temperature. So okay, we definitely want to have a causal model because it's way more stable. But on the other hand, okay, we have to do interventions, and I'm not able to. So how do I continue? Are there any alternatives? And yes, there are some tricks that I can use for purely observational data. And yes, I can also take into account this concept that of interventions and maybe look inside my data set and see if there are any interventions in my data set. So think again about the smartphone. If I would usually fit a neural network to do a certain classification, well, I can just do the first thing that I usually do. I take the data set, I just shuffle it completely and then just build a model, but then I'm losing information because I actually have different environments in my data set. I can just go the other way and not shuffle the data and use this information that I have different interventions. So make sure that my model can generalize well across these different data sets. So, okay, let's go into the first one and let's look at how I can extract causality from observational data. Very simple example. I'm taking a data set with two variables, y and x. I'm just taking a linear model as the underlying generating distribution where y is regressed on x with some uniform noise on top of that, just added to this model. Okay, if I now I have this data set available and now I want to fit a model to that linear model again with additive, let's say, uniform noise, then if I look into the right, in the correct causal direction with x as an input and y as the predictive variable, then I get this nice linear model. And the interesting thing is that if I look at the residuals, it also seems to be quite straightforward. It's just a uniform distribution again. On the other hand, if I would have, again, I don't know what the causal direction is if I have a data set, and that's what I'm trying to figure out. So if I would have done the opposite, so just turn this figure around like I do here, and I fit in the opposite direction, so I use y as an input and try to predict x, then again I get a nice linear model, there's no problem there. But if I look at the residuals, then I see that it's way more complex. So now my residuals become a function that depends on x and y. So it seems that if I go into the correct causal direction, that this is determined by the, let's say, simplest direction. And that's something that is often used, is that the causal direction is the simplest direction to do your fit in. So, okay, causal discovery, there's a lot of different methods available, but usually they can be categorized into a couple of different methods. The first one being independence-based methods. So I can try to reconstruct my Bayesian network with the rules that I know from Bayesian networks, being that some things depend on each other if I know one of the other nodes and so on. So I don't know if most of you saw this university or in or somewhere else, but there are a couple of rules that you can use to determine, for example, if this node depends on this node, if I have measured this node. The other possibility is just to restrict the function class. So for example, taking linear models and seeing within these this mathematically well-defined world, how I can determine the causal directions. And the other one being information-based methods. So that's what I did, for example, here. I just said that, okay, if I model in the correct causal direction, then my model should be sort of the simplest, right? The simplest is something that tells me something about the underlying information. So, okay, this is a bit of an overview of why causality has become a very hot topic again, mainly in deep learning. There are some standard methods available that use linear models. For example, LinGAM is a very popular one. PC builds in, well, fits linear models. Then you have the PC algorithm, which just looks at independence. There are some other methods available as well that have stood the test of time. But now people are looking to more fancier machine learning models. And one of the main difficulty is that, well, what we're going after is this causal network. So what is this causal network? Well, it definitely has a couple of links. So we're trying to map these links. And these links are a sort of feature importance, because it tells us that for us to predict a certain variable, we need a couple of other variables. And that's not something straightforward. For example, if you think about deep learning, well, feature importance is notoriously difficult. It's not an interpretable model. So we need a feature importance to determine what the links are in these DAGs and these causal networks. And there was a recent breakthrough which now allows you to really use deep learning to do causal discovery to determine these DAGs. And the main reason is that somebody in No-Tears, there's a paper called No-Tears, derived a new loss function, how DAG-ness a certain network is. And it basically allows you to combine predicting, making a predictions, building a predictive model, while at the same time constraining your model to be a DAG. So knowing that it can actually represent a causal model. So, but I have to, in the meantime, also say that causal discovery is also something difficult, in the sense that you have to, at the same time, look for this DAG. So you're trying to map the causal structure while at the same time making the predictive model. But when you start from the very start, you don't know what the causal directions are. So in principle, the most general model that you can build is one where you have the complete network of all the connected links, where you have to build a model where every node that you want to predict has all the other nodes as a possible input, which is a completely high dimensional problem, which is difficult to to solve. So I'm just giving these methods here available. They all come down to the same thing, that you actually try to do this. You just model all the possible causal direction. You minimize the loss function while adding this new loss function to it that just says that, okay, you need to look into you need to only consider those networks that actually are a DAG, while on top also imposing that you want to have the simplest directions only, because as I showed you before, the causal direction is usually the simplest direction to make a model. The second main type of approach is to look at invariances. So really exploiting this concept of different environments, looking, not just shuffling the data, but sort of zooming in on the data and seeing if there are any different environments in it. Are there any different smartphones? Or, for example, a case that we're looking at right now is with EEG. There you have the participant dependence, right? If you put an EEG hardware on somebody else, you probably have to rebuild your model. It's very hard to handle. This is usually based on the concept of invariant risk minimization. So the concept of the fact that if you go to a different environment, that if you model in the right causal direction, that your model should not change too much, because many of these causal links remain the same. But one of the difficulties, and I'll come back to this, is that you have to sort of quantify at each point during your fit what you believe what you believe is the score of each of these causal links. So I'm just writing this down in this W matrix. This quantifies from each node in the network what do you think is the probability that it has a causal link connected between two nodes. So okay, let's zoom in on a very specific case that a PhD student of mine focuses on, and that's extracting causality from time series. So the goal here is that you get a multivariate time series and you're trying to extract this causal graph. So you want to determine the causal graph, and you also want to score. So you want to score the possibility that each of the possible links actually represents a causal link, while at the same time also generating a predictive model. The difficulty is, of course, the large space of causal graph. The amount of causal graphs that are feasible are super exponential in the number of variables. Also, it's not entirely clear if you want to use deep learning how you score the probability of a link. As I said, it has something to do with feature importance, but with deep learning, that's just difficult to quantify. And scalability is a big issue, because you start from this big space where everything is in your data set has a plausible causal connection to each other. So you have to build a model in each of these directions, and then you have to find the best model. So if you have many input variables, of course, this doesn't scale well. So that's why a student, Bart Busman, he invented this architecture called NAVAR, the Neural Additive Vector Autoregression Model. And the basic idea is to mainly look at scalability. So scalability is a big issue, as I just pointed out. And their main idea behind NAVAR is to, first of all, restrict the function class. So let's not just use a full-fledged model to do autoregression. Let's restrict it, and let's put the main nonlinearities only where we need them. So we started thinking, okay, where do we need the nonlinearities mainly when modeling a time series? Multivariate time series, well, it's usually the main nonlinearity is in the univariate time series. So if I'm trying to predict, for example, in this case, these are the different variables and the time flows to the right, and these are just the different timestamps. If I want to predict the next value for x in this time series, well, the main nonlinearities are in dependency on the history of x itself. So what we did is we just restricted our deep learning model to capture those nonlinearities with whatever deep learning model you have available, while keeping the different contributions from different other variables as an additive assumption. So additive assumption is just like you have in a linear model. You can have different nonlinearities, but in the end, they just contribute by just summing them up together. So just to make it more concrete, if I'm trying to predict, in this case, the next timestamp, and I'm trying to predict, let's say, y, trying to predict this variable, our model basically assumes that I have additive contributions from each of these individual variables. So for example, I take this thing as an input of a function f. So I'm taking the history here, putting this in a deep learning model. So this can be an MLP, an LSTM, or whatever floats your boat. And in the end, I'm just going to sum them all together. And the advantage is very clear in the sense that I now have a way of disentangling all these different contributions. So this is an explicit architecture. So to make it explicit here, I have the different time series, the history of the time series as an input. So this is X1. I'm using this as an input of this backbone deep learning architecture. And then I'm predicting, for example, in this case, I send a contribution from this time series 1 to another time series 2 to make a prediction. And I'm just adding all these contributions together. So, okay, now I'm at this, I definitely tackled scalability, right? Because I limited the amount of interactions that I'm actually capturing. I'm just looking at interactions between the history of a certain time series, but not necessarily the interaction between different time series. So I can easily quantify what the probability is of or score a causal link. So if I'm trying to score the causality between two variables, let's say xi, and how it influences xj, well, what we can do is we can just go back to our architecture here, run over the whole time series x1, and just look at all the contribution that it sends to another time series, and I can just quantify how much this varies, how much this differs from zero. So for example, I can take the standard deviation. This gives me a quantification of how much this one time series influences the other one. So here, this is an explicit curve of one of the experiments that we did, where you have, we look at our mRNA levels, and you have a couple of variables. So the blue curves is the data, or predictions are the orange curve. And the nice thing, additional thing, is that we cannot just score the individual contributions, but we can even visualize them. So we can even see throughout time, where does this causality come from? So we can see at certain points, for example, here, if you look at the contributions, we see that when you go further in time, when this gene 0, when it becomes large, then this gene 1 and gene 14 start contributing as well, but it doesn't really contribute when the gene 0 levels are low. The main contributions in this case come from the history of the gene itself. So just to summarize, although it looks a simple assumption that we made, it is an essential assumption to extract causality, because on top of, if you want to do causal discovery, you don't just care about making a predictive model that predicts your time series as good as possible. No, you also try to quantify how much each of these variables influence each other. So and this is just one application for time series. We are doing other different applications. So for one group is working on the Horizon 2020 project, where we look at modeling time series coming from earth sciences. So trying to see what the effect is on CO2 sequestration in the ground based on the temperature. We're looking at BCI applications, so trying to avoid participant dependence of EEG signals, or models that work on EEG signals. And then a new project that we're starting in the near future is another Horizon 2020 project, a European project that tries to aims at building a sort of automated lab using causal models. So we're looking at building reactors that extract CO2 from the air and try to store it into stone. If you would try to do these experiments, it would take way too long if you want to do all the possible experiments. So we're trying to accelerate this by building predictive models while doing experiments. And you can only do this if you have causal models, because as I said before, if you have interventions or if you're doing experiments, you have to build causal model, because these are the other one that are actually able to represent these interventional distributions. So this was just a very small overview of the things that we're looking at. Definitely, if you're interested, just give me and drop me an email and just let me know. Thank you.
All right. Thank you, Janus, for this deep dive into causal machine learning. It's very interesting. Thanks for sharing. I'll kick your screen of the sharing thing. Yeah, there we go. So there's a few questions on the chat. I'll read them out loud, and then hopefully you can answer them.
Mhm.
How Navar? So Henrique asks how Navar deals with non-stationary data. Is it still necessary to perform the same procedure as in traditional time series forecasting?
Well, we focus on stationary. So we assume that our causal graph that it's fixed, right? That it's well determined. So we assume that it all comes from the same process. Well, it's stationary, but on the other hand, we also exploit, of course, the direction of time.
All right, cool. And then Istvan asks, great presentation, super relevant for market research. Are you aware if the econometrics literature on causality,
Yes.
diff, potential
Yeah, yeah.
outcomes, regression, continuity, synthetic control?
Yeah, that's a very good question because in causality there are two frameworks. There is and these sort of clash. These are two worlds that clash with each other a bit, but they are proven to be equivalent to each other. So indeed, you have another framework which is the potential outcome framework. This is very useful indeed in economics research, and it rather tries to look at individual cases. So, for example, in medicine, what if I give somebody a treatment and I give somebody medicine? What it will be the potential outcome of this one participant? We are rather concerned with the distributions, right? If you look at, for example, earth sciences, you rather care about the distributions. We don't care about individual treatments, for example. So these are very connected to each other. They just use a very different language. But I would say, this is, a discussion. The DAG framework is a bit more general, and I find it much easier to work with, though it's not that practical in some cases. But yeah.
Okay, cool. Thank you. I think there are no further questions. So thank you, Janus, for this great presentation. I understood from you earlier that you had to leave after the presentation, so you won't be coming back at the end of the data science meetup. But thank you very much for participating, and good luck with
Thanks for
the follow-up of the research.
opportunity.
Yeah,
Thank
my
you.
pleasure. Thank you. All right, let's see. Next up is Geert, I think. Geert, I'll add you to the stream. Welcome, Geert.
Hey, hello.
I'll also add your slides to the screen. So you're going to talk about deploying ML models and APIs to Kubernetes using GitOps. So completely different from the last one. Maybe you'll also talk about DAGs, but then there's some other kind of DAGs than mathematical DAGs, I think. Anyway, thanks very much. I'm looking forward to your talk. You can go right ahead.
Okay, thank you. So good evening, everyone, to this part of the evening. As indeed stated, we look at deploying ML models and APIs, but really basically anything you want to Kubernetes using a GitOps approach. So who am I? My name is Geert Bake. I work at Kronos. Now, I'm not a data scientist or data engineer or something like that, but I often work with the teams that have to then later deploy things like models and so on in an enterprise context, and then think of things like security and so forth. And my work is mainly in the Microsoft sphere. So if I'm giving some examples of how these people do, or how we do ML models, how we create them, typically within those products I'll talk about. Of course, if you want, you can follow me on social media channels. If you want to ask a question later on, feel free to do so. Now, what we look at is, first of all, what is GitOps? Define a bit what it is, compare it with some other techniques on how you do, for instance, model deployment. And of course, you also need some software. These are called GitOps operators. We look at which ones are available on the market and how well known are they, and are they really used in production by people. And then I will take out one example, which is the product which is called Weaveworks Flux, which is gaining quite some traction. And we look at how that one works. Now, of course, GitOps. It's of course a term, like you have so many terms in IT, that is very broad, and you can give really different kinds of meanings. And of course, in essence, if you look at it from, let's say, a top level, it is rather straightforward, right? You have configuration files that you of course store in Git, and then you have some other system that takes these files and that is going to use them to deploy infrastructure, applications, and so on. So it doesn't have to apply to something like ML. It doesn't have to apply to something like Kubernetes. It can be used in a very broad context. Now, in this case, what we are looking at today is really more narrowly focused in a Kubernetes context. And there are some specialized pieces of software that are used to do GitOps on Kubernetes. And of course, at the Kubernetes level, if you have worked with that before, yes, if you like it or not, you will have to create YAML files and deploy that to your cluster. So you will store these, of course, in a Git repository. You can organize them the way you want in folders and whatnot. That's totally up to you. And once they're in a Git repo, what you'll actually do is have some process running, which is typically based on some kind of schedule. And in essence, what that process is doing is nothing more than every 5 minutes, we pull everything from the Git repo and we apply everything we find to the cluster. And yeah, some people already sometimes joke with it and say, I can write my own GitOps software because I just create a shell script that does this every 5 minutes and it's done. And in essence, they are right. And that's essentially what GitOps is. But of course, the software that we'll use, and you'll see in a moment, you have many more bells and whistles to, for example, control things like dependencies and so on. And so that's something that they will add. Now, important in the case of Kubernetes is that this software, this GitOps operator, as we'll call it later, it will run inside your Kubernetes cluster. So it doesn't run outside of the cluster. And that's an important aspect that I'll come to later as well. So if you summarize this, first of all, you're going to have to work completely declaratively. So everything will have to be declared in files. If you use GitOps to deploy, let's say, a model to your Kubernetes cluster, there's no command you can run. You will have to have a file somewhere that is then used by this GitOps operator. Yeah, a second thing, of course, is that all the desired state is versioned in Git. I think that's clear. The approved changes are applied automatically after some pull request, for example. That's okay. And an important aspect is, of course, that you have this continuously running software agent. So not like with a pipeline that runs, for example, when triggered. There's a software agent running continuously, in this case, in the cluster, to ensure correctness and make sure that the declared state or the desired state that you have in Git is matching the actual state on the cluster. And that concept alone has also many advantages over, let's say, traditional ways of working. Now, traditional is between quotes, because of course most people still use, and that's okay, traditional deployment pipelines, and pipelines in themselves will not go away. And of course, these pipelines are driven typically by some CI/CD system. Let's say you're using GitHub workflows with actions. You know that these actions are used in jobs and within steps to execute tasks. And an important aspect of this is, of course, that these systems, they do not force you to work declaratively. You can do whatever commands you want within those tasks. So if you want to run shell scripts, all kinds of commands, run kubectl, do a Helm install, whatever you want to do, you can do that. You're not restricted from doing that, which is good. It's flexible, but on the other hand, it might also bring you some trouble later. Another aspect of these systems, so the deployment pipelines, is that, of course, these systems, they typically run outside your cluster, and you need to configure credentials to your clusters. If you have only a couple of clusters, that's fine. But if you have many clusters dispersed, maybe at the edge of your network, maybe in store locations and so on, that can get quite tricky. And of course, these systems, they also have to connect to the Kubernetes API server, and they have to push the configuration to the API server, which is okay in most cases. But yeah, the pull mechanism might be that GitOps is using. It's pulling the contents within the cluster and then deploying it, can be an advantage. For example, I'm working with a customer right now who is thinking of using Kubernetes in store locations, so physical stores across Europe. And they will indeed run some smaller version of Kubernetes there. Probably it's going to be K3S or something like that. Having to have the line of sight to the API server pushing all the configuration changes to these clusters across Europe can be a little bit tricky, and a pool model can be an advantage there. So they're also looking at GitOps mechanisms to configure these systems in the stores. Another issue that you might have with pipelines is that, of course, they are changing the state gradually. Whenever they run, they do a little bit of a state change, which also means that if, for example, they fail, and you have to know, okay, what's the state? How do I repair it? How do I fix this, and so on. And also, when your cluster fails and you'd like to rebuild your cluster, if that's what you really need to do, because other ways to prevent that, of course. Yeah, rebuilding the state of such a cluster, if you have multiple pipelines going into that cluster all the time, is also not so easy. With a GitOps approach, where your entire state is described in your Git repo, it's simply a matter of deploying a new cluster, connecting the Git repo to it, and having the state come back to your cluster. So there are several advantages of the approach. Although a disadvantage, some people are saying, is that indeed the fact that they cannot do anything with a simple task, everything has to be done declaratively, can cause you some headaches as well. So of course there are pros and cons to everything. Another thing, or another advantage that a lot of people see in GitOps, is that they really force you to, of course, separate what you do with building your software. So let's say, just call it the CI part of the creation of software, the testing and building of your code, creating container images. You have to separate it from the deployment part. For GitOps, you use that for deployment, and you will have to separate it, which is typically also a best practice to do that. And by the way, Git, of course, is used in both cases, but you really should use Git repos for your development work, should be separate from the Git repos that are used for the GitOps part. And yes, the vendors, they always introduce all kinds of terminology, and they sometimes like to call this the immutability firewall. Let's just keep it at there's a separation between the two, because you're forced to work that way, right? Now, of course, when you're deploying these, because basically you're just deploying YAML all the time, like always, to your Kubernetes cluster, you will of course have to verify correctness. So tools like kubeval and Conftest should be used to verify the correctness of your YAML manifest before, of course, you do a commit, that the operator that's running in the cluster works with valid manifests, of course. Now, yeah, you need some software in your cluster that does the actual work of the deployment, because you're going to do deployment with GitOps, and that's just an operator. An operator, maybe you're familiar with that. Kubernetes operator is an application-specific controller, and of course, yeah, Kubernetes is built as a collection of controllers that work all the time based on new data coming in. Now, of course, these GitOps operators, they are continuously running, as we said. They run all the time in the cluster, and they work on a schedule. That's an important thing. You define the schedule for the different pieces of software that you want to deploy to the cluster. So there's not one schedule. You can set different schedules for the different softwares that you are going to deploy. The important thing is it always runs on that schedule, which also means that if there are troubleshooting tasks to be done on the cluster, something is not working, you of course have to be able to pause this continuous sync. And most GitOps operators will allow you to do that. And if you want, you can also configure a webhook, of course, when your code is changing, for instance, that you directly take action in your cluster. Now, as I said earlier, yes, you can build your own GitOps operator by just creating a shell script that does these simple actions I talked about earlier. But of course, these tools have additional features. For example, in the previous slide, I actually showed that. Well, let me go back to that. Monitoring, tracing, logging, of course, has to be a part of every tool that you use for deployment, and they offer that typically with the Prometheus integration and so on. And of course, they also provide management tooling like CLIs and UIs. Not all have both. Most have a CLI, or all of them have a CLI. Some have a user interface as well, a web UI, for instance, to do operations on the cluster. So that's one thing that they do. But also there are additional features. For example, pruning. That means that when you remove some YAML from the Git repo, that the software is removed, let's say the model is removed from your cluster when you remove it from the Git repo. Or also dependency management. If, for example, your software depends on other pieces of software running, you can model that with most of these operators, which is, of course, something that's really welcome, because if it's just a bunch of YAML files, it starts to deploy at the same time. That's not what you want. You want to introduce dependencies. And there are also mechanisms to automatically update the cluster or the application when the image is changing. For example, if you have deployed a new, or you built a new model and you're packaging it up as a new container, a new version, that software can see this, the GitOps operator can see this and deploy the new model right away in your cluster without you having to intervene. Not all of the softwares that I'm going to talk about have this feature available. Now, well-known examples on the market today, I think that the two ones you see there, Weaveworks Flux, which is the logo at the top, is very well known in the market. It's an open source tool you can just use, and they also have a commercial offering that you can buy from them. So that one is gaining quite some traction. The other one, Argo CD, is also quite well known. That's the cute icon there at the bottom. That one is used also quite a lot, and we're also seeing quite some integrations of Argo CD and other systems. For example, I think, if I'm not mistaken, GitLab, for example, if you use GitLab for CI, GitLab can also be used for deployment, and they also can integrate with Argo CD. They have this natively built in. You can use that in their tooling. But other vendors, the well-known vendor Rancher, which was bought recently, I think, by forgot the name, but not that important. They have a tool called Fleet. So you see many other offerings coming on the market. But I think the two top ones there, Flux and Argo, they are the most well-known within this space. They might not be well-known compared to other tools, but within this space, they are quite well known. Now, I'm often working with enterprise customers where things are not going always that fast, right? It's not so easy to introduce completely new tooling and functionality. So the question I often get is this mainstream enough? Is this mainstream enough for me to start using it reliably? And where's the support if we need it, and so on? Well, what I can say to that is that popularity is increasing. If you look at the latest CNCF survey, which was done, I think, a couple of months ago, you can see there that the people they asked what are you using as tools for deployment, that things like Argo CD and also Weaveworks, it's creeping up in the statistics. So its popularity is really increasing. Of course, they both are CNCF, so Cloud Native Computing Foundation projects, and so they are both Weaveworks Flux and Argo CD are both part of the CNCF. And what we also see, which also means that it's really gaining traction there, it is starting to be offered by cloud vendors as well. For example, we offer managed Kubernetes. In the example of Azure, they have this hybrid play, which they call Azure Arc. You can basically bring any cluster you have running at the edge on premises in other cloud vendors. You can bring that under Azure management, so to speak. That's Azure Arc enabled Kubernetes. And they offer a GitOps feature there as well. That's in public preview today, so you can play with that if you want. AKS, so their managed Kubernetes offering, will also have GitOps enabled soon. That's now in private preview. Now, Microsoft did not build their own software. They actually use Weaveworks Flux as part of their offering, so they work together with them, and they now use version 1 in their Kubernetes offering. And later, because they're working on version 2, the people at Weaveworks, later it will also be version 2 that will be integrated. So it's really getting into mainstream, but that doesn't mean that everybody is using it. Most people that I'm working with today, most companies I'm working with today, they're still using pipelines, the traditional deployment approach, and that's fine, and nothing wrong with that. So if you look then at Flux, I have to explain something about the terminology here, because indeed I already said to you that Flux v1 today is the current version. They're working on Flux v2, and it's nearly finished, not quite there yet. but it's really at a good level. And if you start looking for Flux, you might also find on Google the GitOps toolkit. Now, what the people of Weaveworks have done is they have taken version 1 and they have componentized that version. They broke it up into multiple pieces. And that is actually called the GitOps toolkit. And the GitOps toolkit is actually Flux version 2 as well. So maybe a bit confusing, but if you're looking at Google, you're searching for the GitOps toolkit, you'll actually come to the entire explanation of what it does. So what are the components of this GitOps operator? What do you have to have in your Kubernetes cluster to start deploying anything, and including these ML models, right? Well, first of all, you have to be able to define sources. So you have to tell this operator, where are the files that I'm going to actually use? Pretty straightforward. That's usually Git repo, no problem there. But there are other examples of sources as well. For example, a Helm repo. For those that work with Helm on Kubernetes, they'll know what this is. There's also a Helm repo where you can store Helm charts, right? That's also a source. And even an S3 bucket or Azure Storage, for instance, can even be a source. If you really don't want to use Git, you can store it in a bucket as well. I haven't asked them if they support something like Dropbox. I hope not, but in theory, that's also possible. So you first have to define your sources. And once you have your sources defined, you can start thinking about deploying to your cluster using YAML files. In the case where you're using YAML files, you're probably going to just point to a folder, and that folder contains a bunch of YAML, right? The customize controller is used for that. And for those who know a bit about Kubernetes, customize is a tool to indeed customize, with a C in that case, your YAML files before deployment, with customize build. But you don't have to use customize. So if you just have YAML files in a folder you want to deploy, you use the customize controller for that as well. The reason they call it like that is that they're always using customize internally. So they use the customize tooling internally, for instance, to order the deployment of the YAML files. So if you know something about Kubernetes, when you deploy to a namespace, you first have to have this namespace, and then you can deploy in it. Well, customize by default, it will first deploy namespaces and then deploy the rest. So they use this for internal ordering and so on. But if you want to use customize and add a customization.yaml to the folder, you can do so. This thing will pick it up and will use customize build before deploying this. When you're used to doing that in pipelines, like in GitHub Actions and so on, they typically call that baking your YAML with customize or something else. That's actually this step. Now, most people that I work with that deploy software to a Kubernetes cluster, most of the time they are using Helm charts, of course. That also means that a GitOps operator needs to have support for that. There's no way around it. You need to support that. Otherwise, it's not serious. The Helm controller is used for that. But of course, because you cannot actually run the Helm command to install a chart, right? You cannot do that because you need to work in a full declarative fashion. This Helm controller will pick up configuration files that tell it how to proceed. So in that configuration file, you will say this chart version has to be installed. These are the values to override and so on. So you have full control of Helm deployments by this system. And it's actually much better than in a pipeline, because in a pipeline, if the Helm deployment fails, what are you going to do? Are you going to configure something like rollback? Does that happen automatically or not, and so on? This software is really taking care of that. And you can control what happens, what needs to be done, for example, when a Helm installation fails, that you go back to the previous version and so on. There's a whole life cycle can be controlled from this Helm controller. So quite some more control over Helm deployments with this system. And of course, we cannot forget that we want to have notifications, because we don't have enough today, right? We want to have them in Teams or in Slack. And of course, the notification controller can be used for that you have some visibility, because these things are just running in the cluster. They're doing their thing based on these config files. You want to know, of course, what is happening and what is going wrong inside. Now, what about updates? For example, you build a new model, as I said earlier, a new model, a new version, a new tag for your container image. What do you do in that case? Well, the first thing that you can do is just, of course, modify your YAML files. You go into your repo, you do a pull request, you modify the tag of your container. Once it's approved, it will be deployed by the GitOps operator. If you have to do that for everything, for example, even for a patch release or something like that, okay, might be a bit cumbersome. So within Flux, Flux has this capability. It can actually scan an image repository for changes. So that's a place where you store your Kubernetes images or your Docker images, basically. It will scan for changes, and then based upon some kind of range or filter that you set, you can tell Flux, for example, if you use semantic versioning, you can tell Flux, hey, if the patch level changes, so the third number in a semantic version, if the patch level is changing, then automatically do the deployment for me. I'm not gonna modify my YAML files, just do it for me. Now, what Flux will do in that case is it will not directly modify your deployment. It won't touch what is running because that's something that's working imperatively. You don't want that. It will actually reach into your Git repo and modify the YAML file itself by modifying the tag of the image. Because Flux has read-write, you can configure it with deploy keys, SSH keys, that has read-write to your repository. Now today that's available in Flux v1. In Flux v2 it's not available yet. That's actually the part that's not entirely finished. So last time I checked was on the 11th this month. They were 80% complete. There's a roadmap somewhere where you can track this. And you can play with this alpha version if you enable it during your Flux bootstrap phase. I'll talk about what bootstrap is later. So that's basically what GitOps is. So that means that if you are using that to deploy an ML model, for example, yeah, we need to find a way, or we need to just make sure we have these kind of customizations and sources and maybe even a Helm chart or whatever to deploy the ML models. Now, the teams I'm working with in a Microsoft, let's say, environment, they are often using the Azure Machine Learning service. And yeah, it can get kind of tricky here because, yeah, people who are working with that, they're used to working with that environment, and they have the ability to deploy models to a Kubernetes cluster completely on their own. They don't need to have a pipeline or GitOps or whatnot. They don't need that. They can deploy to Azure compute anything they want. So they can, for example, deploy a model to Kubernetes, but also Azure Container Instances, Azure Web App. They can even deploy these today to Azure Functions, so use the serverless model to deploy their ML models. That's something I think which is in preview at this point in time. And usually what they are doing is, of course, they're working with notebooks. They're using Python. They can just write some Python code to, for example, build a container image. They can do that with 2 lines of code. If they want to deploy their model to a Kubernetes cluster, an inference cluster, they can just write, let's say, 4 or 5 lines of code, and the model gets deployed to that cluster. And what we see is that in the beginning phases, that's often the only thing that they do. And then only later they're creating pipelines and automate this entire thing. So it's sometimes a bit of an issue if you talk with them to make sure that they can move off this completely manual way of working, and of course move to a pipeline and maybe a GitOps model that I'm talking about today. With most teams today, I can tell you this, it's just a pipeline, right? It's not yet GitOps because they're not really completely comfortable with that. It's still something that we have to do there. So yeah, that's great. That also means that they are used to working in a specific way with Azure ML, where Azure ML does the following thing. So you tell Azure ML, hey, I have an inference cluster, which is AKS. And from the moment you mark AKS or any Kubernetes cluster as an inference cluster, but it will of course be AKS in this case, the Azure ML workspace will deploy a front end to it already. I didn't do anything. I don't have GitOps here or a pipeline. From the moment I'm saying this cluster is my inference cluster, this thing gets deployed to it automatically. And this is actually the front end to all the models in the back end. So all the inference requests for the models that you deploy will go through this front end. And this front end takes a lot of responsibility. For example, it does SSL, it does logging to something like App Insights, it does logging to storage, Azure storage, and it even scales up your models in the backend. So of course, when we talk to the data scientists who use Azure ML, they also want this component deployed if you're using pipelines and whatnot. And then, of course, you are going to deploy your actual models, and that's this. The model is just going to be deployed as a container, right? Nothing special about that. You know this. For Azure ML, it's very specific. They build a container for you, although you can work with custom containers. But if you don't, you give the container building process a score.py, so a scoring file that does the actual inferencing or scoring. It builds a container for you based upon what they think is a best practice. That one will listen on port 5001, and the front end is just going to, based on a model service name that you set, it will route the request it gets on the front end. It will route this to the backend models according to this service name that is in there. So of course, if we're going to use GitOps to do this, we have to follow a similar approach. Now, for, let's say, to not make it too complex, I only look at, in the example I have in a moment, I look at doing the model deployment only with GitOps. But we can also do this with the front end if we really want to. Although there are some issues, but I'll come back to that later in a moment. With some customers, we sometimes even just deploy the models like this without a front end in front of it, but then we have to provide our own security to it, SSL via an ingress controller, or do SSL and authentication via an API management tool of some sorts. And we have to also do our auto-scaling ourselves, because as I discussed, the Azure ML front end is doing auto-scaling of the models in the backend according to the amount of requests it gets. So if we are removing that front end, yeah, of course, we have to do the scaling ourselves. We can use a horizontal autoscaler for that, which sadly is going to be used. By default is using CPU. You would have to tweak it to use other parameters. Now let's do a demo, but it's a screenshot demo because we are a bit limited in time. So I'm not going to do clicks and run commands because that would take us too long. And actually, these are all commands and YAML files, so it's not that interesting to look at really when I'm doing it for real. So let's take a look at how we do a deployment with Flux v2. And just for reference, I did this a bit myself. Now, again, I'm not a data scientist, so I'm not doing these kind of things. But if you look at what the data scientist is doing in Azure ML, for example, to package a model, I commented this out now, it's just 2 lines. This creates an image. So they can, for example, say, and I just used a toy ML model, MNIST. You all know this, hello world, I guess. And there I'm saying, okay, deploy version 0.0.1 to a container repository. And then we can just say, okay, let's deploy to AKS, for instance, and just, I was right, 4 lines to deploy to AKS. So we don't want to do this. We want to do it with GitOps. Yeah, what do? We first need to make sure that our cluster we use for inferencing has Flux installed. That's really simple to do. The people from Weaveworks provide a Flux command line interface, and the Flux command line interface, I see I'm going over time, I'm nearly there, is going to do the actual deployment. That's just this command. And we're using a repository here called Kubernetes Bootstrap. Okay, that's just a repo, nothing special about it. The first thing I need is a source. A source is this, just a YAML file. And there I'm saying, okay, I'm calling it Kubernetes common. And this is the Git repo that contains the source. Really, really simple, right? I mean, this is not complicated at all. Then, of course, I need to deploy something that's in that source. We talked about that. That's a customization. We just create a customization file like this. Flux will pick this up. The customization controller will pick this up. And here I'm saying use this source. You use a folder in the source called deploy. But wait a moment. You first have to deploy this Kubernetes secrets thing before you do the deployment. Dependency management is done again using YAML files and specifying what you want to do. The actual deployment folder is just a folder with other folders, and those folders then contain the things I want to deploy. For example, in this case, I want to have an ingress controller, Nginx, no problem. In that folder, there's a YAML file that in this case does a Helm release. I think you see where we're ending up. Whenever we want to do a deployment, we just have to add folders, add some YAML, and the thing will pick it up and do the deployment. So in this case, this is how we control how we do a Helm release. We just say deploy like that. That's the name of the chart. You can see that there, chart ingress nginx. Deploy it for me and override these values. That means I now have my baseline of software I need. Now I want to deploy the model. Now that's this here, that's just a couple of YAML files. I'm not going in there. You can always go to my GitHub repo, so github.com/gbake, go to Kubernetes Common. You can look at them, what they are, in fact. And to actually deploy this, we just need to add this here. So once I have done that, from the moment I create this customization, this is how we do that, and we save the output of this to a Git repo, what happens is now that this Flux operator will start deploying the model and will continuously look if it needs to do something. So if I change the YAML files, for example, to go to another version of my model, I just change it in my model, in the YAML files, and it will pick it up and deploy it. That's the only thing that I have to do. And of course, you have some control here to see, did it work? I can check what are all my customizations. And the ML model is in there. It was deployed properly. And I can trigger the syncing. I can suspend the syncing. I can resume the syncing. That's actually everything that we're doing in our daily work. Now, in this specific case with Azure ML, I would really like Microsoft to create an Azure ML operator for Kubernetes, because the problem is that the Azure ML workspace is doing everything imperatively and interactively, is modifying my cluster, and I actually don't want that. I would like to have Azure ML indeed deployed where the data scientist can do its work, but I would want to create or configure my cluster using YAML files and using an Azure ML operator that then links this all up to the Azure ML workspace. That's not there today. There are some ideas around that, probably, but we're not quite there yet. So that's also why today we are typically using the GitOps method for the entire cluster configuration, all the dependencies for your models and so on. We're using it to deploy APIs that might use these models as well. But the models we are still using, a lot of times we're still using a pipeline, traditional one for that, until, of course, there's improvement where we have an operator where we can do all of this. So I hope this made it clear that GitOps is just an alternative deployment method. And if you use other ML systems to create your models, you might have a better fit. Several solutions, and yeah, it's gaining popularity. So check it out and see if it's something that is useful to you. And sorry, Chris, I went over time.
Yeah, thank you. Indeed, you did, but that's fine. It's all good. Thanks for sharing. This was super interesting, especially for me as an engineer myself. I liked it a lot what you had to share. We're gonna have a little bit of time for questions, but we're not gonna spend too much because indeed Stijn still has to go, and he's a young father, so he needs to go to bed early otherwise. So no, but quickly, Henrique asks, so hey, here, thanks for the fine presentation. What do you think of Kubernetes deprecating Docker? Is there really just a simplification in Kubernetes, and does it not affect our current deployments?
Yeah, it is really a simplification because you don't really need that Docker shim, which they were using in Kubernetes to work with the Docker system. So the fact that it's removed from it, it's really good, and it's not really an impact. What we are not noticing an impact at customers when we move to a version that is not using Docker shim within Kubernetes. So there are some small edge cases here and there, but for most people, there's no impact, and it's a good thing.
All right, cool. And then a question from Bart. He says, thanks for your presentation, Geert. Do you have any recommendations for deploying in an A/B test setting? Where would you define which models to deploy in parallel? I guess listening in container registry updates would not work in such a case.
Yeah, first of all, Microsoft themselves with Azure ML, they are allowing you to actually deploy multiple models and versions of that, and then having percentages of traffic going to the different ones. What we also do sometimes is, for example, using progressive delivery controllers to basically say, I want to do something like canary, blue, green, and so on. And for example, the one from We've Worked, which is Flagger, so the Flagger tool is fully compatible with GitOps as well. So you can actually do these blue, green, and canary releases with that tool in a GitOps style. Yeah, if that answers the question. And I think, indeed, listening to the updates indeed can work in combination with that. That they automatically go to a new version when there's a new container image in that repository. Yeah. Oh, we don't hear you.
I was muted. It's a classic mistake. Thank you, Geert, for your time. It was very interesting. So now it's time to switch to Stijn. I'm going to add him to the stream. Geert, I'm going to remove you. Stijn, welcome for the final talk of the night. We went a bit over time. I apologize for that, but Stijn, feel free. I mean, you have your 20 minutes plus 10-minute Q&A. So I would say go right ahead. I'll add your screen to the stream as well.
Yeah.
There you go.
Chris, let me know if you can see the screen, if it's popping up.
I can, yeah.
Okay, cool. So hi everybody. So today a different third topic, yet another different topic on the agenda: how bees act as an IoT sensor and can help solving biodiversity. So just 2 quick words on myself. Indeed, like Chris pointed out, I'm a father of 2 lovely girls, and I don't think that they are fully asleep yet. So they came into my room 10 minutes earlier. I hope that they are finally getting asleep. As a daytime job, I'm a consultant working in Accenture, focusing on all things analytics. I am a skier, and actually, Chris, we used to know each other first back in the days when you would still go onto the slopes and with your snowboard.
When we were young, when we were very young.
Hopefully, after the pandemic, we can do that again. And back in the summer, I've launched a podcast focusing on sustainability and social entrepreneurship called the Entrepreneur Connect Show. So for today, there is one consulting slide, the mandatory one, and afterwards I will go to the topic at hand. I think it's important message. So what we are seeing happening is that we've lived through the globalization in the back before the millennium. We have as well lived through the digital transformation era, which is actually still ongoing. But now there is a different shift that's happening, and I think it's close to my heart, and I think it's also close to other people's heart, where you're switching towards acting for instance, climate change, which is a super important topic, and we all, let's say, have a certain responsibility to share. Yeah? And as a company, for instance, from Accenture, we can do only as much. All other companies and organizations are also taking the lead, forming partnerships, and helping in the next 10 years to work towards, for instance, the sustainable development goals by 2030. And to achieve that, I really see that there is quite some momentum in the market. Clients are asking advice around this, how they can accelerate decarbonization. And I think as consultants, we have the obligation, we need to help them, and we need to be part of the game. And voila. And today's presentation is part of that context. And we worked with a client, biodiversity, specifically on that. Voila. So that's my 2 minutes of consulting, and now let's get into the stuff. So biodiversity, as you can see, it's really a big problem worldwide. And here you see the different species organized by category with a risk on extinction. Yeah, you see, for instance, palm trees as the highest risk. You see amphibies. You see coral reefs, sharks, all with very high percentages of risk of being, let's say, up until the point of being extincted. And it's also with plants, trees, not only with the animals. And it's broader than only biodiversity. So that's why referring earlier to the Sustainable Development Goals, back in 2015, I think there were around 180 countries that came together that pledged to agree to these Sustainable Development Goals. And what you see here, for instance, at number 15, life on land, and that's biodiversity, as well as 14, life below water. And then you have the usual suspects, like climate action, number 13, or number 7, affordable and clean energy. And actually, it's a super massive, big problem. It's some people have called it monstrous problems because it's so interlinked, so global. For instance, here, it shows the link in this diagram between your climate change that's impacting, for instance, your habitat destruction, impacting your biodiversity. So all of these things are interlinked, and obviously they are now also starting to identify whether big pandemics like the one that we're now seeing is also linked to, for instance, the lack of biodiversity. And the premise here is that due to the destruction of biodiversity, people are starting to live closer to the forests where the viruses are still living on the animals. And there are so many viruses out there in, let's say, in the jungle, where normally human people would not come close by. However, by creating roads through the deep forest, we are getting more in contact with these unknown viruses. So let's zoom in a little bit on the bees aspect. If you look, this is the map of Europe, just to illustrate a bit the context. Every year there is a decline of the bee population to a certain degree. For instance, in Belgium, it's more than 20% decline, and there is a couple of root causes related to that. One is habitat loss. So because there is much less open space for bees to shelter, they don't have enough, let's say, habitat. Climate change is also impacting that because their behavior is changing due to that. Pesticides is an obvious one, used often in agriculture, and then diseases. So there is certain diseases that are spreading between the bee colonies, and then suddenly impacting and impacting them quite significantly, actually. So enough to give a bit of context on the problem that we are looking at. Now, biodiversity, it's a company that we worked with, and that has for years now, I think more than 7-8 years, has been working to solve the problem on biodiversity. And they're using bees to do that. And here you see a picture of a site of Knokke, where biodiversity worked with the city of Knokke together to improve the local biodiversity in that space. For instance, by installing bees on the site. And what you need to know is that bees are very good for improving and pollinating the different flowers, so that there is more plants that are growing thanks to that. For instance, the fruit that we eat, it's mostly thanks to the pollination of the bees that this is happening. So what biodiversity is actually doing is installing beehives, the bijenkasten, on these sites, and then releasing a lot of bees over there to ensure that the pollination is increasing. And on top of that, they are installing as well some new vegetation and plants to have the necessary growth related to that. But even better, if you look, the bees, they are very hardworking, and they actually cover a quite big area when they are looking for their food in the flowers. And again, this is the example of the city of Knokke, where in a diameter of 1.5 kilometers, they are doing their search. So they are actually covering a wide area and collecting the pollen from the various plants and flowers. Now, the clue, what biodiversity has been doing for the last years is the following. So they've developed a tool called a biomonitoring tool. And what they're doing, they're bringing the pollen that has been captured in the beehives. They are bringing that to a lab, and they're analyzing that in the lab on 3 dimensions, a couple of dimensions. They are checking for heavy metals. In the pollen, they are checking for the biodiversity, how many species of plants are captured in the pollen. And they are checking for another dimension. I forgot it. Let me quickly check. And they are checking for pesticides as well. So it's about the heavy metals, it's about the pesticides, and the biodiversity that they can find by analyzing in the labo the results of the pollen that have been captured in the pollen trap, that's how they call it, in the beehive. And let's just show an example. Let me see if we can get this to work. Of their collaboration that they have with SPA, the company that you're all familiar with that's delivering water. Let me play the video.
Zie je dit bijtje? Ze komt uit het beschermingsgebied van het natuurlijk mineraalwater Spa. Zo'n 13.000 hectare of 26.000 voetbalvelden groot. Het werd gecreëerd in 1889 en zorgt dus al meer dan 125 jaar voor heerlijk natuurzuiver en gezond water. Het bijtje woont er in een van de korven, geplaatst door Spa en biodiversity. Bijen zijn immers een ideale manier om de kwaliteit van het milieu en de biodiversiteit te meten. Ze tonen aan dat de beschermingsmaatregelen in het watergebied van Spa bijzonder efficiënt zijn. Er werd namelijk geen vervuiling aangetroffen in het gebied. De biodiversiteit is er dubbel zo groot als in landbouwgebieden. En het aantal bijen steeg sterk. Van 160.000 naar 400.000. Een natuurzuiver milieu zorgt dan ook voor het uniek natuurzuiver mineraalwater Spa. Voor ons vandaag, maar ook voor de komende generaties. Want als de mens het water beschermt, beschermt het water de mens.
All right, so this is just to give you a bit of a flavor, of what type of solutions that biodiversity currently is putting into the market. Now, what's the challenge with this kind of solutions is that it's still limited and not really scalable. So the geographical coverage is limited, and you need to always install a site. I go to the site, install the beehives, and then extract the pollen from the pollen trap, go to the lab, analyze the results, etc. So there is a lead time challenge, not scalable, etc. So how can we solve for that? So the clue is we need to be able to calculate an eco score without having the bees on site. And like I mentioned earlier, it's about heavy metals, it's about the pesticides, mostly due to farming, and it's about plant diversity. And all of these, they give a score from bad to good in an aggregated way. What we can do, let's look at what's the data that we have at our disposal. On one hand, we have the historical data from the existing beehives that were installed through the various clients of biodiversity. And we have as well map data. Yeah? So we have map data from the Marine Land Cover database. It's a European Union aggregated database that is showing very well on every location what's the type of land cover behind. Yeah? For instance, on the second screenshot here, you can see in the region of Spa, where the current beehives are installed for the biomonitoring tool for Spa. There you can see some red zones, which is the more the houses and the local town. And then on top you see the big green area, and it's actually there where the water is collected and the beehives are installed. So this is the existing data that we have. Yeah? Now we have as well the map data for full Belgium, and let me just quickly show on how that's looking like. You have the red spots, which is more the towns and the cities. You have more the green spots, which is the forest. And you can even see the Forêt de la Soigne and Zoniewoud near Brussels. And you have the more orange, yellow part, which is more agriculture-like. And this Marine Land Cover database, it's actually providing a legend, yeah, that you can work with as open data. So with that, we can actually predict the eco score for any given location. So as an input, we take this historical data that we have from the various clients where the beehives have been installed, and we then take the map. And what we can then do is predict an eco score on any given location on the map with an algorithm. So let's show an example of what's the application that you can actually build with this data. So we've built a prototype for them, which is showing on the map, and in this case, the client is navigating on a map where they can now drill down on a specific zone, and then you can see the eco score across the 3 different dimensions that we have mentioned. And so again, you can search for any location, zoom in, let's say the green areas are already the ones with a good eco score. It might be interesting to see what's behind it. You click on this, and then you can go to the details. And for every dimension, you can see the various risks associated with this. Now, how is this actually working from an analytics perspective? So on the website, it's a combination of the map data, it's a combination of the risk scores, it's a combination of the historical data, and then an analytical engine that is behind it. So the eco score is consisting out of the 3 dimensions. The data that we have for the heavy metals, it's split into 7 different metals for which the labo has captured the data in the past. And they also have the concentration for every heavy metal linked to that. And the same is for the pesticides. I don't know by heart how many pesticides they are capturing, but there is, for a variety of pesticides, information available, and then as well the concentration level. And then what's also available in the data is how many species that were discovered. So if we plot that, the first input, let's say, is the historical data on the land cover around the beehives. Think Spa, think Knokke, where all of this data is available. And then this is put in a regression model to estimate, actually, in this case, heavy metals, one of the 3 dimensions, to see if we can estimate that. That's basically the training data. And what we're going to do is then take any random point I've taken as the example, the city of the town of Tiele, where I'm currently living. You enter that into the model, and then the model can provide you an estimated concentration in this new area, let's say Thielen, in an absolute amount. In order to put that into a perspective, any kind of a general distribution, in order to be user-friendly, we've put that into a normalization function so that afterwards we have a normal generalized score for metals. And we do this for the three various dimensions, and then we should have a good eco score. Currently, this is something that we have a prototype of. However, we want to now bring this to the market. Yeah? So together with biodiversity, we are searching for partners that are willing to invest in making this a reality. Yeah? Obviously, the business model there can be interesting for a couple of players. Think, for instance, water producers like the Water Group. They would like to know on any given location on the map, what's the risk of contamination with certain metals or with certain pesticides. Yeah? Because what companies like the Water Group today are doing is they need to take samples, go there, and then measure it themselves. However, by deriving based upon the biodiversity data, they can imply that, let's say, at a lower cost. So what we are now doing with biodiversity is the tour de la table. We are checking with certain potential investors to see if they want to invest to make the prototype a reality and build the first MVP. To wrap up, I think this is something where data can really play a role. Exactly. We can pioneer with diversity in making an impact, and then hopefully into production with some of these clients. And if you want to know, well done an interview. Michael on the opening question.
Cool. Thank you very much, Stijn. I think we're still waiting for the first questions to come in. More in general, and I don't know if you can answer this question, but do you think machine learning was really, how do you say, is a critical component in this chain, or do you think if you just did descriptive analytics and try to understand where the bees are at the moment, would that be good enough, do you think?
We've looked at different methodologies, because what you have today is you have a couple of beehives that are spread throughout Belgium. And one way of deriving the information at any given location is by triangulation. However, you don't have enough data points to do that. Your results would be totally skewed because of the different patterns that you have on the surface. It would not work. Descriptive, you don't have the data available, because you need to convert, let's say, the landmarks into an eco score. And by just providing the information and the descriptive information that's available on the landmarks, you don't have the insights on the eco score. And that's what you can then do with the regression model, is you can derive that by a prediction. So I think it's an important component to make it work. Yeah.
All right, cool. Let's wait a bit until we see some questions popping up. There's always some delay in YouTube, so there might be some more questions coming.
Yeah, I'm happy to take questions offline afterwards as well.
So in the meantime, Stijn, can you tell us how is your show going? Who's your next speaker?
I did interview Karen Boet, the CEO from Bcode. Do you know Chris? B-code.
Yeah, well, I don't know her personally, but I know who she is. Yeah, yeah.
So Karen Boers could be interesting. Yeah, I will publish it in a couple of weeks, 2 weeks time, I think.
Exciting. All right, I see there's no further questions. If you want to contact Stijn, his contact details are here. So stijn.gijzemans@accenture.com. Stijn, also for you, thank you very much for this talk. It's a bit of a change from our usual talks. So it's super interesting to see that data science is not just useful for the typical churn prediction models or whatnot, predictive maintenance, but it's also a useful tool to protect our biodiversity. So thank you very much for this refreshing view. And with that, I like to wrap up this meetup. We went 10 minutes over time, but I guess that's okay. Our next meetup is somewhere in February. I don't know which date exactly. Let me quickly look. It's going to be February the 9th. So that's coming up quite soon. Where we will have someone from U Hasselt, Jan van der Bussen, talking about distributed data intelligence. We'll have Dirk van Ifte from BioStrand talking about biogenetics processing, and Geert Verstraeten from Python Predictions, and they released a data science library on GitHub called Cobra, I think. So that's the list for the next meetup in February. So I guess we'll see you all there. And until then, I would say happy coding, happy machine learning model building and whatnot. Thank you all for being here with us. Thank you. Bye, guys.